name is Ron Lajoie. I'm a various officers in the National Space Society, but today I come to you as a fellow space tourist wannabe. I'm also a space systems engineer. I will not mention for what company, but they're about $900 million overall. Next chart, please.
I just got a hold of Will.
What am I talking about with honeymoon cruises to the moon? I'm talking about honeymoon cruises to the moon. I'm talking about Gopher and Isaac and Julie meeting you at the gate and all singing Love Boat and Kathy Lee singing Ain't It Fun. This is a big space hotel floating between the Earth and the moon. It's a one-week trip. It's a cruise. It's a one-week trip. This is a luxury space hotel. First, I must say, all the problems we've just talked about have partially been solved. So you have to put on a bit of an imagination hat and think forward into the future when we've made some progress here. Let's see if I can do this. Okay, here we go. There'll be some cruise specials. There'll be, how would you like to see a lunar eclipse or a solar eclipse from space while you're on the way to the moon or coming back from the moon? The nice part about a lunar cruise is that you're always within sight of a large body, either the Earth or the moon. Unlike a trip to Mars, which is 6 to 9 months where you see nothing but blank sky and a sun, here you're constantly seeing something pretty to look at in addition to your food plates. You have the moon, you have the Earth, and the Earth is rotating. Something you won't be able to get from low Earth orbit. There will be space hotels long before this exists. But low Earth orbit, you've seen it already in the NASA videos. You can't see the whole Earth. You have to come out to the moon to see the whole Earth. Next chart. What were these? What will the cruise ships look like? I'd love for them to look like this nice boat, but we don't have Star Trek technology yet. However, and also, at least for spacecraft, the boat shape is not ideal as a pressure vessel. But it will look like a space hotel with some engines on it. The size we're talking about, the engines probably will not even be noticeable. So it'll look like some space hotels. Here's some ideas that have shown up recently. One on the right is Shimizu, if I'm saying that properly. The other one is an American company examining that. This is way beyond Miracore. This is, though, I'm glad to hear Rick Tomlinson is also thinking of rotating spaceships. One of these might be Rick's future hotel in space. The requirement is the same. A space hotel, casino, whatever, has the same basic requirement. It's to keep people in space and treat them very well for about a week. The nice part about a trip to the moon and back is it takes a week. So once you have your space hotel and it's already geared towards a regular tourist traffic, all you have to do is find some way to get it to the moon and back. I believe that the Earth orbiting space hotels will precede cruise ships by several decades. And the nice part is all the bugs, the basic bugs of providing water and food and all that stuff will be worked out. This is a big issue, and to rotate it or not rotate. Zero G can be fun. Obviously, by that example there, which is Pamela Lee's Lovers in Space art, you get to swim around. It's fun. Just ask the astronauts on the shuttle. They actually have a fairly cramped space, but they love going in and they love swimming through the tunnels. On the space station, they have a bigger block because they have a lot more volume to work with. This type of space hotel, you'll have all those type of facilities. And most likely, we will have zero-gravity hotels first, much larger than, in terms of internal volume, than the shuttle. We'll have zero-gravity tennis courts and all that good stuff. But zero gravity can be annoying, as I think Shannon Lucid lost her shoe for 3 months because it floated away. It's annoying when you can't find something you need. Just think of eating breakfast and someone asks you a question, you look back at your plate and your fork's halfway across the room. So, there's also some of those adventures aren't that fun in zero gravity. Eating and drinking, especially thinking about this on a daily basis, eating and drinking and sleeping and showering and all sorts of other laboratory type of things can be eventually a pain in the butt. And for a tourist, when you wake up in the morning, you probably just want a nice cup of coffee. And you don't want to have to drink it with a straw. It'd be nice to be able to sit back and do at least some earthly type functions. And when you want to go into zero gravity, you can. That's the one benefit of a rotating spaceship. Zero gravity can also be dangerous. Number one, there's no swimming because a swimming pool becomes a drowning pool. In fact, you can actually drown. If you're not careful, you can actually drown yourself in the shower. Now, right now, the shower has been on space station is waiting in a habitat waiting to be built. If that is a danger. They actually have to put on a face mask and breathe oxygen while they're taking a shower. That's pretty annoying. And I won't even describe what they have to do to go to the bathroom. There's also zero gravity is a major issue on the space station about the airflow, circulation. Without gravity, whether it's artificial or Star Trek, convection has to be forced. And if you're not careful, you can create voids where carbon dioxide can accumulate. Before you know it, as you're floating along, you run out of oxygen. That's a health problem. Also, as we know, this is some things we discussed earlier with the perceived risk of space and the barriers that we have to overcome, is there is a problem with prolonged exposure to microgravity. This will not be a problem for tourists because they won't be in space very long. Their biggest issue in zero gravity is probably what we kindly call space adaptation syndrome. I won't describe it. You know what it is. But it is a serious issue for the staff. You know, the space shuttle astronauts are going to have the same problem. The staff is not going to be conducive to hire staff to serve in a hotel if they've got to worry about significant health problems. So how do we cure that? Well, von Braun came up with a solution a long time ago, as did Stanley Kubrick and his probably 50 others going back for the last 100 years. This is extremely simple. This is physics that goes back to the discovery of the wheel. It's been with us for at least 20,000 years. It's called you spin it and you create artificial gravity. I would think the space tourism industry wants it. I hear Rick Tomlinson certainly saying it, and for all those other reasons, I certainly would like the option of having gravity for certain basic functions. And then the nice part about the rotating space station is in the center it's zero gravity. So there are places you can go and have the zero gravity experience. That's it. Excellent. This is obviously a crude drawing, but it gets the general idea across. As in the scale that I'm talking in terms of a sample rotating space station. It could be a wheel, as you've seen in the 2001 drawing, or an actual disk, where the thing is an actual solid disk. To make these numbers come out really easy if it's 100-meter radius. You can use a smaller radius, but what happens is you have to increase the rotation rate to get the same G-load. And a lot depends on what G-load you want at the bottom. If you want Earth 1 G gravity, then you have to rotate this thing at 3 revolutions per minute, or once every 20 seconds. If you want the bottom to be Mars gravity, then you rotate it a lot less. It's linear. That's one nice thing. The physics of this is extremely simple. There was a study done in the 1960s that often gets repeated why rotating space stations won't work. It was done with people in a small room, so their feet were, the people's feet and their heads was in a significantly different artificial gravity zone. When you have something this large, the variation in gravity is extremely small. Their study concluded that once you get above 4 revolutions per minute, you start to suffer significantly. Once you get below 2, no one has any problems. So this is 3, this is in the middle. Again, this is it's a matter of scale. And I think as we go along, further study will prove that this is probably more than adequate. And again, this is, if necessarily, we can reduce the size of it. By having a multiple layer space station, you have inner levels with lower gravity. You can have Venus gravity, you can have Mars gravity, you can have lunar gravity. And the windows are actually on the side. We're looking on this edge on it. Okay? It's just like looking at one of these other drawings I showed you. And the windows are on the side. So think of where the engines are on the right. Again, it's the sample. This side's going to the moon. That side has a view of Earth. So you always have a view from every window you go to of Earth or Moon as you receive or go forward. I'm sure there'll be, by the time this gets built, there'll be lots of other ideas. This is, again, just a concept. This is a front view, pretty boring, but it gets the idea across. Earth gravity at the outer rim. Venus gravity is 0.9. It's at the bottom is 90 meters, so you have essentially a 10-meter level. Mars is quite a bit inside. It's at 38 meters. So you have all that inner space, which could either be vacuum connecting elevators, or it can be used as other levels for storage, or you can even have other levels for other gravity environments. And then you can have an inner level as for the moon, and then you have your zero gravity and your docking base. The classic 2001 Blue Danube type of docking is still the best way to go for this kind of thing. And I'm sure we'll play that when we dock with these kind of things. This type of space station, space hotel, doesn't necessarily have to go to the moon. My guess is something like this will exist before then. We will have rotating spacecraft with different gravity levels in Earth orbit. And then we'll just stop an engine. The nice part about a space cruise liner is we can take advantage of a lot of other people's work. Let them take the bugs out of this. Let them figure out exactly how much you have to spin in, worry about the cold rolls and acceleration. Yes. Our main challenge is how do we get this thing to the moon? How many of you have come across some email traffic prior to the purchase of Mir, or at least the lease of Mir, as a concept of saving Mir to put Mir in lunar orbit? I'm show you how many people heard that. Since the partial amount of energy needed is the same as the energy I need to get my space hotel, I'm going to run you through some numbers here. First, I'm going to train you in being a rocket scientist. In one page. So here it goes. This is actually high school physics, except for some integration, which requires senior high school or freshman college. Acceleration is thrust over mass. And thrust coming out of the rocket engine is the mass flow of the propellant, which is, in engineering terms, symbol we use an M with a dot over the top, times the exhaust velocity, how fast you're throwing out this mass. Very simple. And the exhaust velocity in America, anyway, Europeans stick with velocity. We like to call specific impulse and divide by gravity. This is not gravity on the moon. This is the gravity conversion factor, which is always equal to a standard sea level gravity on this point. The change in velocity, and our speaker at lunch today talked about delta V. The change in velocity is just the numerical integration of acceleration with time. That's the one and only college course you have to take. Acceleration, substitute those numbers in, get down to this one. The delta V at the bottom here is the gravity times the specific impulse. Those are constant. You can assume those are rocket parameters. The integration of m dot over m is college freshman. It always equals the natural log of mass. And that comes out to the very end. And the beginning and end conditions are your beginning mass and your end mass. So you get down to the classic rocket equation, which is the change in velocity is directly, linearly related to the specific impulse, how fast you're throwing the propellant out, and the natural log of the ratio of your initial mass to your final mass. Next turn. To put Mir in orbit, you'd have to do two separate maneuvers. I'm just going to talk about the first one, which is sending it on its way to the moon. This is the other half of the rocket science is orbital mechanics. This is just looking at the classic minimum energy trajectory. The delta V required is 3,100 meters per second. If the space shuttle main engines, the specific impulse is 465 roughly. If we put a nice big nozzle on it in space, we can probably get it up to 480. There's some technology that can push it over 500, but this will suffice. You take that number, you take the delta V number, you back out what that mass ratio is. It's 1.93. Right? That's the ratio of the initial mass, which is your space station, your engine, a big tank, and all that fuel. That's your initial mass. The final mass is everything except that fuel, if you do this in a single burn. And that's described there. Now, trust me on this one, for these type of missions, Boeing has done a lot of these type of studies, except they're not pushing hotels, unfortunately. The amount of structure associated with the tank and the engine is about 10% of the tank and the engine and the fuel. That allows you to make that a fraction, and you get a very simple equation. The mass of the propellant equals the mass of your payload, in this case it's the station, times that little bit of math there. Since we know that mass ratio is 1.93, and we have 10%, very simply it comes out as a little over 1. That means that the amount of propellant you have to throw out during your burn is the mass of your space station. The Mir, which is a fairly small space station, is about the same as the space shuttle. It's 100 tons, 100 metric tons. You have to throw that out. That was the station I showed you earlier, the concept for that. The space station is about the radius to Mars, to the Mars level. So that's probably 1,000 metric tons. Now we have to throw out 1,000 metric tons of propellant. We have, right now, the only way to do that is to get it from this plane. If you multiply that times $5,000 a pound, that's a lot of money. Needless to say, it's not going to be a trivial task. We'll definitely, by the time we're doing this, we'll definitely have taken advantage of the water from near-Earth asteroids, because we're going to have to find a cheap way to get the type of propellants we're talking about. Or we're going to use nuclear rocket engines. If you have a nuclear rocket engine, the speed at which you can throw the exhaust out is about twice as much. It's about 960 seconds. That mass ratio, because it's a natural log, it actually is better than double, or better than half, so the mass ratio is 1.39. What comes out is the propellant comes out to, instead of being a little over 1, it's actually 0.4. So it's a 60% drop. That's the good news. The bad news is, by using a nuclear rocket stage, you have to add a radiation shield. And that tends to be about another 10% of the propellant mass. What you do is you put that between the tank and the space station, or your payload. And that's a significant mass that you're dragging along. But you're still saving at least half your propellant. So that's an option. And when you're done, with the nuclear rocket engine, you can stick it in the Van Allen belt and it'll happily live there with all the other radiation. No one will ever notice it. This is a one-time event. The key thing is this is a one-time event. You don't want to have to push the station to the moon, get it back, and have to slow down and push it out again. So the next chart, please. What we want, and this chart is courtesy of Hughes lecture, what we want is to somehow put a space station, a space hotel, space cruise liner, in a permanent orbit between the Earth and the Moon. And you can see here that by doing so, say for these special cruises when you get to see a solar or lunar eclipse, you have a beautiful view from the middle section, right in between. You'll actually cross you'll actually be in the shadow of one another. The problem is, next chart. The moon keeps moving away. Orbit mechanics is really, a lot of classic orbit mechanics is based on a single gravity point, which in this case is the Earth, in your spacecraft. It's called a two-body problem. The reason this thing looks like a crazy ape is because you're coming in to approach the moon and then swinging around behind it. And essentially the moon is deflecting the orbit, and you're orbiting the moon for a short period. Then you leave, and you're now once again orbiting the Earth. Well, that works well. It's called, NASA did this for the Apollo mission, and I think we would do the same. It's called a free return. In other words, we boost out from the Earth, and if we don't do anything else, we're coming back to the Earth. That's obviously the safest way to go. Problem is, when we get back to the Earth and we swing back around, the moon is no longer where we would like it to be, and we'll just go out and orbit dead space. And so what we have to do is some kind of maneuver to correct it at some point along this orbit, or multiple points along this orbit, to adjust this to swing to where the moon will be by the time we get back up. Next one. Here's the basic approach. We have, in terms of how I plan to set up this problem, this is an orbital mechanics problem. I have the software, I have the basic initial and boundary conditions, and here's the unknowns. I have the starting condition of be at the far end of the moon, called the periloom, the closest point of the orbit to the moon. Start there, come back in, swing around to the perigee of the Earth, go back up and get to the moon again. From a numeric standpoint, I can break it up essentially into a problem such as this. But the unknowns are how high I have to be from the moon, how high I have to be from the Earth, what that inclination is in terms of the planes of the Earth and the moon, how many burns I have to do, when those burns occur, in what direction they occur. If this was a simple planar problem, an orbit itself in just one body and another body with a flat plane, now we've involved two bodies. If you heard about the Hughes operation where they sent a satellite to the moon, what they did is they swung around the moon in such a way that they did what's called a plane change. They changed the orbit from essentially this to this. And they did this because the orbit they launched from was like a Cape Kennedy type orbit, which is 30 degrees. And they needed to get it into geosynchronous orbit, which is 0. The amount of energy required to use an engine is enormous. By swinging around the moon, they essentially got a free plane change out of this. Now, they did have to use propellant to get it to the moon, and through a lot of analysis, they determined that it was going to take less propellant. And propellant on a satellite is its life. It was going to take less propellant to swing it around the moon than to try and do a propulsive burn. That same type of thing has to be factored into here, is that the optimum amount, the minimum amount of fuel needed to adjust this orbit may involve some tricky maneuver. That's the key thing. For this cruise ship to be commercially viable, that initial burn to get it into its orbit is not the big issue. It's the repeated burns. On every pass, every 6 days you have to waste some propellant. That's, for every 100 pounds or 200 pounds of propellant you have to burn, that's 200 pounds less people you can bring. So the key answer here, which I was hoping to have that answer today. I'm just beginning that work. But don't worry, this is my future career, so we'll have lots of time to talk about this. The key answer is, the key goal is to find that number, how small amount of fuel that is. And then we can decide if this concept's worth pursuing. Where am I now? And this is have the basic approach has been formulated. Again, the boundary conditions. I have the numbers, but I won't bore you with those and the constraints. I have the tools I need in terms of the software I need, and there's just a lot of numerical work to do and a lot of tweaking to do. And I understand that Bigelow Aerospace, which was looking at hotels in space, is also now interested in lunar cruising, so I definitely would like to talk with them about this. And I'd certainly like to talk with any of you later on. we're about getting close to finishing it. If you'd like a copy of these charts, they're available they will be, as soon as I get back, at that website, at that address. And there'll be more information coming. How many of you read the story? If I had more time, I was actually planning to read this, but the story I left. Well, they all disappeared. Somebody read it. How many read that short story? I left it on the bulletin board. It's called The Honeymoon Cruise to the Moon. It's actually a story about what types of things you can do in space, in a facility such as this. Right there. Oh. Thank you very much.
This looks like the alternate side of the
This wasn't that to Mars? Or is the other one to the moon as well? Yeah. Yeah, the Mars? Oh, no. Well, one problem with ion drive, that works well for putting the Mars cycle, because in the end what you want is this big orbit for Mars. For this particular orbit, this crazy this egg-shaped orbit, you can't use low thrust, because in the end you'll be in a lunar orbit. You'll be orbiting with the moon around the Earth. You don't want that. You want to be constantly repeating between the Earth and the moon. So you need a high thrust, short burn to do this. Sure. My life goal was originally, since I was born in 1962, I wanted, by the time I was 100, to be able to fly the spacecraft to meet Halley's Comet on its next return. Now this is my current life ambition.